Hello folks, welcome to the latest edition of the Physics Corner. I'm your host, Dr. Christopher Sorolla, and this is a series of videos where we show how to set up and solve simple physics problems. Today we're taking a look at Faraday's law, or an application of it, and change of magnetic flux. So let's suppose we have the following. We have a 9-volt battery connected in series with an inductor and a resistor, and of course a switch. So the switch is open, nothing's happening. Close the switch and wait a while, and the current increases from 0 to half an amp within 2 milliseconds. Now, just to make this clear, we're going to assume that this is greater than the 5 time constants of an RL circuit, which means that we are well over 99% of the maximum voltage that will be across the resistor at the end of this time. So if you're wondering about how that might work, we have a different video talking about RL circuits. I'll just make that comment so it's understood how this is working. All right, so let's go with the numbers that we do have, though. Let's talk about the average change of current over time. That's not exactly how we would best describe it, but we're going to run with that for the purposes of our problem. The inductance, and again, we're calculating that assuming the current is changing at a constant rate, and the change of magnetic flux. So, while these are not going to be exact numbers officially, this will give us a good, run-of-the-mill ballpark sorts of figures. So let's get started. So Faraday's law has an interesting statement. It says that the change of magnetic flux, or more officially the negative of the change of magnetic flux, yields voltage. Or conversely, if you have a voltage, you connect the circuit, you can get a change of magnetic flux. Okay, where's the change of magnetic flux going to happen? It's going to occur in our coil, in our inductor, which is symbolized right here. Now, we're not going to end up using the negative sign in this particular set of calculations. The negative sign's purpose is to talk about what we sometimes call a back EMF. We're not worried about that particular issue here. It's not going to be relevant for what we're talking about in this particular problem. So if I'm ignoring the negative sign, it's because it's not going to affect the calculations we're doing. But there's also something else that comes up if you write this. You can rewrite this in such a fashion as the negative of the inductance multiplied by a change of current over time, like that. And that leads us into some interesting statements. So let's go ahead and take a peek at what we have. So first off, we have a current that changes from 0 to 5, or 0.5 amps, in 2 milliseconds. Let's calculate that. So change of current over time equals 0.5 amps over 0.002 seconds, like that. And when we do this, even though it looks like it's 0.5, which thinks that it kind of indicates it might be a small answer, notice we're dividing by such a much smaller number in the change in time here. Another way to think of it is this is basically 500 divided by 2, or 250 amps per second. Okay, so there's the change of current. Now again, average change of current is what we're doing here. So we're making a very crude calculation in this case. But let's think a little bit about what that says and what it means. So this is something that tends to confuse students a little bit when we write it this way, because the thought is we must have a change of current and a change of time separately. And in my example, I did do that. But the change of current over change of time is its own quantity. It's its own thing. And it sounds kind of strange because we don't have a separate name for that. Well, we have encountered that, or you have encountered that kind of idea many, many times. Something as simple as velocity. It's a change of displacement over change in time, right? So if you wanted to calculate an average velocity, find the change of displacement, change of time, divide them, you've got an answer. It just so happens we have a name for that. We call change of displacement over time a velocity, or we call, say, a change of velocity over time an acceleration. And so that's something that sometimes is done, right? But we don't have to give names to every single change we ever encounter, and that's not done here. So it is okay to have this, to talk about a change of something like this over this as its own separate answer. That's the legit thing. There's no problem with that. We just, if we wanted to give it a new name, we could. Physics people just have never done that. Okay. So with that comment out of the way, let's go on to the next step. It says, let's determine the inductance. All right, so leaving off the negative sign, we have EMF, or the magnitude of EMF, if you prefer, is equal to inductance multiplied by this change of current over change in time. Now again, I could use the individual values for change of current and change of time because we've got them, but it's a little bit more instructive to maybe do this the other way around. So let's solve for inductance, which means I need to divide by this. So inductance is then the magnitude of the EMF divided by this quantity, change of current over change in time, like that. So EMF was 9 volts, and my change of current over time was 250 amps per second. And again, this is akin to doing something like calculating with a velocity or an acceleration. It's okay to do that. I keep mentioning this because it is one of those things when I took physics way back long ago, it was something that confused me to no end. I kept searching for, well, there's got to be an individual change of current or a change in time, and how do I get these numbers? And sometimes they're not given. Well, they don't have to be given. If you have a rate of change of current over time already, that's all you needed. And that's all we needed here. And when we do this calculation, let's finish off the problem here. We get 0.036 henries, or if you prefer to write this way, 36 millihenries. So that would be the inductance. All right. Last one to talk about here today is the change of magnetic flux. Now, again, in this particular example, we do have a change of time available. So we can calculate an average change of magnetic flux. Again, the magnitude, the absolute value of the EMF, will be the change of magnetic flux over time, like that. Or if we multiply both sides by delta T, the change of magnetic flux equals the EMF multiplied by delta T, like that. That's something that's kind of interesting to write, by the way, is that that's what magnetic flux is. It's a voltage multiplied by some change of time. Okay, and that's an interesting thing that comes out of this. So this is a wild thing to sort of think about. It. Voltage, an EMF, by changing that, you're basically creating magnetic fields when you do that. And that's a hint going forward, or looking ahead into the future for you folks a little bit, is that when you change a voltage, you're changing really an electric field ultimately, right? You're ultimately creating a magnetic field in the process. Well, you've also seen places where it goes backwards. By changing a magnetic field, you can create an electric field. That was the Ampere's law stuff that you've studied by now. So there's sort of a tie-in, there's sort of a symmetry, if you will, between how changing one kind of field can create another kind of field. That's an idea you're going to encounter a lot going forward. Let's put in our numbers. Enough of the soapbox. 9 volts and 2 milliseconds. If you prefer, we can write it this way this time, just to show the difference, like that. And we get 0.018. Okay, we have volts multiplied by seconds, so volt seconds, if you will. Okay. Now, that's one kind of way to express the unit, and that's perfectly legit. Volts and seconds, certainly okay to say that. But let's think about another way that we could express these units, just to say them. This is magnetic flux. Magnetic flux in general comes from this kind of formula, right? Magnetic field multiplied by a cross-sectional area and a cosine between the two vectors that these two have with them. This doesn't have any units. Magnetic field comes in Teslas. Area comes in meters squared, right? So if we wanted to, we could also write this as 0.018 Teslas times meters squared. And it's also something that's kind of interesting to state it this way, to say that Teslas multiplied meters squared is the same unit-wise as volts multiplied by seconds. So a little bit of unit analysis hinting for you there. But the couple of lessons that come out of this example, one is that a change of magnetic flux will give you an EMF, or turn it around, an EMF of voltage can be used to create a magnetic change, specifically of magnetic flux. Now notice it's change of magnetic flux, not magnetic flux, change of magnetic flux, right? The second thing is having a change of something over time, or a change of one thing related to a change of another. They don't always have their own individual names, but you can still talk about them. So it's okay to say, oh, the change of, say, current over time is a certain number. Or, and we could do this, we didn't, but we could do this, the change of magnetic flux over time can be construed as a certain number. And by the way, if you think about it, we did. That's what we called 9 volts. All right, folks, I'm going to wrap it up there. Our technical support comes from Sydney Gautreaux and Sophia Turner. These videos are funded by the University of Mississippi and University of Southern Mississippi. I am your host, Dr. Christopher Srolla from Hattiesburg, Mississippi. Thanking everybody for your attention, as always, and clear skies.